Right, let us now talk about cathode rays and cathode ray tube. Now consider a metal surface containing a large number of free delocalized electrons. The electrons cannot escape because they do not have enough kinetic energy to overcome the nuclear attraction. However, when the temperature of the metal is raised by heating, the electrons gain enough kinetic energy and escape from the metal surface. This process of release of electrons from the surface of a heated metal is called thermionic emission. We can use an electric circuit to generate electrons through thermionic emission and then accelerate these electrons towards a positively charged target. What we need is to produce electrons that move in a vacuum with no wires. The setup consists of a vacuum tube, inside of which is a highly negative cathode and a highly positive anode connected to a high voltage DC supply about 600 volts. When the cathode is heated, the electrons of the metal atoms are excited and move a little away from their nuclei and then back to their positions. But when the DC supply is switched on, the electrons are repelled from the negative cathode and attracted to the positive anode traveling in the vacuum. So we get a beam of electrons traveling in a vacuum, reaching the anode and thus completing the circuit. The rate of thermionic emission depends on the surface area of the metal, temperature, and the type of metal. When the surface area is increased, the rate of thermionic emission increases due to increased number of electrons that are affected. When the temperature increases, the rate of thermionic emission increases, and this is because more electrons will gain enough kinetic energy to break free from the metal surface. The rate of thermionic emission is different with different types of metals. This is because different metals require different amounts of energy to release electrons. The rate of emission can be increased by coating the metal with metal oxides, which decreases the minimum energy required and therefore release electrons at a much lower temperature. Let's talk about cathode rays. Cathode rays were discovered in 1879 by William Crookes while conducting an experiment on electrical conductivity through gases. The apparatus used for his experiment consisted of a glass discharge tube, now called the cathode ray tube or Crookes tubes, and a high voltage source. The discharge tube was sealed at both ends and was fitted with thin pieces of metal electrodes at each end. It had a side tube fitted with a stopcock that was connected to a vacuum pump. Crookes observed that at low pressure of 0.01 atmospheres, when a high voltage of 10,000 volts is applied across the electrodes, current starts flowing inside the tube. To further study the behavior of this current, he punctured the anode inside the cathode ray tube and coated the glass tube behind the anode with a fluorescent material such as zinc sulfide and repeated the experiment. This time, he noticed a bright spot on the coating behind the anode, which then confirmed two things. One, the current consisted of an array of invisible particles, some of which could pass through the perforated anode. And two, these rays were emitted from the cathode and moved towards the anode. Therefore, these rays were named cathode rays. Right, let's talk about the properties of cathode rays. J.J. Thomson experimented further with these rays and discovered some of their properties. He observed that when a solid object is placed in the path of the cathode rays, it produced a sharp shadow of the object. This implies that the cathode rays travel in a straight line. When an electric field was applied to the setup, the rays were deflected towards the positive plate. The rays were also deflected when a magnetic field was applied to the setup. He therefore concluded that the cathode rays comprised of negatively charged particles, which he named electrons. In another experiment, Thomson observed that if a metal foil is placed in the path of the cathode rays, it becomes hot, and this implies that the rays possess kinetic energy. And so, cathode rays are basically a beam of electrons produced at the cathode through thermionic emission and accelerated towards an anode in a cathode ray tube. Let's talk about the cathode ray oscilloscope. Now some modifications are made to the cathode ray tube to develop the cathode ray oscilloscope, or the CRO. The CRO is built up of three main parts. The first part, which looks like the cathode ray tube but with a few modifications, is called the electron gun. This part produces electrons by the process of thermionic emission. The second part is named the deflection system and causes the deviation of the electrons from their normal straight line path according to the voltage applied to the plates. It consists of two pairs of plates named X and Y plates. The third main part is the fluorescent screen. This screen is coated from inside with a layer of a substance that is sensitive to electrons. It gives a bright spot at the position where the electrons strike. The three parts are then enclosed in an evacuated glass envelope. Let's look at each part in detail. The electron gun is a modified version of the cathode ray tube. The first modification is made to the anode. The anode here are two hollow tubes instead of a closed plate. This is to allow for the passage of the accelerated electrons through it to the deflection system. The second modification is adding a grid, which is a metal ring that is connected to a negative potential. This negative potential is controlled by a controller button on the interface of the CRO. This button is the brightness. Adjusting the button will adjust the negativity of the grid and hence the amount of repulsion between it and the electrons. This in turn controls the thickness of the electron beam, which ultimately affects the brightness of the spot on the screen. The second part is the deflection system, a system that is responsible for the deflection of the beam of electrons from its original straight line path. The deflection system consists of two parallel horizontal plates called the Y plates. The Y plates are electrically connected to the interface through two openings called Y inputs. This is where we apply our signal or the voltage to be measured. The signal can be as simple as a DC battery or as complex as a sound captured by a microphone. They are also connected to a button to control the amount of deflection by the Y plates. This button is named the Y gain, or sometimes the voltage scale. For example, let us connect a DC battery to the Y input. This will apply a voltage on the two plates so that the upper one will be positive and the lower one is negative. This causes a deflection of the electron beam upwards towards the positive plate. And if we reverse the connection of the DC battery, the plates will reverse their potentials and the beam will be deflected downwards. This appears on the screen as a spot that is lower on the screen. But if the battery is removed, the bright spot will be at the center of the screen because there is no deflection. The second part of the deflection system is the X plates. To understand the X plates, we must remove any signal from the Y plates. Unlike the Y plates, The X plates are not controlled by external signals or inputs. The X plates work by a signal from inside the CRO. The value of the signal is controlled by a button on the interface. This button is named the time base. As long as the time base is off, there is no voltage applied to the X plates and the spot is in the center of the screen. When the time base is having any value, an inside signal from the CRO named the sawtooth voltage causes the deflection of the beam across the screen left and right with high frequency. This will appear on the screen as a horizontal straight line. The third part of the CRO is the fluorescent screen. The screen is covered from inside with a material that is sensitive to the electrons. When the electrons fall on the screen, it gives a bright spot in the position where the electrons hit it as seen from the outside. The screen is divided into squares like a graph paper so that we can take our measurements, as we shall see later. The scale of the screen is controlled by the Y gain and the time base buttons, while the intensity of the spot is controlled by the brightness button. Let's see a few examples when different signals are applied at the Y input. In the first example, we remove all signals from the Y input and the time base is off. This will show a spot in the center of the screen, and this is because the beam is not deflected anywhere. In the second example, there is no signal applied to the Y input, but the time base is now turned on. This will change the spot to a horizontal line. And this is because a sawtooth voltage from the inside of the CRO is applied to the X plates. It causes the deflection of the beam left and right across the screen with high frequency of about 50 Hz. This appears on the screen as a horizontal line. In the third example, the time base button is turned off. The horizontal line becomes a spot at the center. Then a DC voltage is applied to the Y input by connecting a 3 volts DC battery. Because of this connection, the beam of electrons will be deflected upwards towards the positive plate. If the Y gain button is adjusted to 1 volt per square, the spot will appear on the third square on the screen because our battery is 3 volts. In the fourth example, we reverse the connection of the battery. This in effect reverses the potential of the Y plates. The top plate is now negative and the bottom one is now positive. The beam is therefore deflected downwards towards the positive plate. So the bright spot will appear on the third square on the screen, but this time below the center of the screen. Remember, the time base which controls the X plate is still off. The fifth example, we replace the 3 volts battery with a 5 volts battery. This will make an upward deflection, but this time the deflection is greater because of the larger potential difference. Again, the Y gain button is still adjusted to 1 volt per square. The spot this time will appear on the 5th square. In the 6th example, we still have the 5 volts battery, but the time base button is now on. This will change the spot on the square number 5 into a horizontal line because now we have an upward deflection by the Y plate, and at the same time the X plates cause continuous left and right deflection across the screen. This causes the horizontal line. And if we reverse the connection of the battery, the line will now appear at the bottom. Changing the scale to a smaller value will cause a longer line. In another example, the X plates are now off. Then a 5 volts AC supply is now connected to the Y input. Recall that AC is a current and voltage that continuously reverses. This causes the beam to deflect up and down rapidly due to the rapid reversing of the voltage and hence the charge on the Y plates. Because the time base is off, no horizontal deflections are observed. The signal will be seen on the screen as a long vertical line in the center of the screen. The value of the voltage is the measure of the amplitude, which is from the center point of the screen to the top of the signal. Here, the screen shows it is 5 volts. And for the last example, the AC voltage is still applied on the Y input. But now, we will turn on the time base button. This will change the signal into a sine wave. And this is because the up and down deflection caused by the AC on the Y plates is accompanied by the horizontal deflection across the screen caused by the X plates. This will be seen on the screen as a wave. Let's talk about the uses of the CRO. First is CRO as a voltmeter. Now we have seen that a CRO can indicate the voltage of a DC or AC supply. This is connected to the Y input with the time base off. The sensitivity is then adjusted, for example 1 volts per box. The distance from the center to the bright spot gives the voltage. Using the CRO as a voltmeter is advantageous because it has an infinite resistance and therefore no current is lost. It can also measure both direct and alternating voltages. It responds instantaneously, unlike conventional voltmeters whose pointers keep swinging about a point. It can also measure large voltages without being damaged. The CRO can also be used in determining the frequency of an AC signal. The signal is fed into the Y plates of the CRO with the time base on. The time base control is then adjusted to give 1 or more cycles of the input signal. The time t of the signal is then determined by relating the trace of the signal on the screen with the time base settings. The frequency f can then be calculated as f is equal to 1 over t. Let's take a few examples. Now we find the time period and the frequency here. Each wave is 2 cycles. For the first one, the first cycle ends here. The time base is set at 1 second, and that means 1 second per division. So these are 1, 2, 3, 4 divisions. So 4 times 1 second gives us 4 seconds. So period is 4 seconds. Frequency is given as 1 over t, so 1 over 4, and that gives us 0.25 Hertz. The second one, the first cycle ends here. These are also 4 divisions. Time base is set at 0.5 seconds, so 0.5 seconds per division. Period t will be equal to 4 times 0.5, giving us 2 seconds. And f will be equal to 1 over t, which is 1 over 2, and that gives us 0.5 Hertz. Finally, third one, time per division is 1 millisecond, and that means 1 over 1,000 seconds, or 0.001 seconds. Again, 1 cycle is 4 divisions. So t is equal to 4 times 0.001, which gives us 0.004 seconds. Frequency will be equal to 1 over t, 1 over 0.004, which gives us 250 Hertz. One last example. The figure on your screen shows a trace of an oscilloscope for an AC source. If the Y gain is 1 volts per centimeter and the time base is 2 milliseconds per centimeter, calculate A, the peak voltage of the AC signal, and B, the frequency of the AC source. Remember, Y gain relates to the vertical displacement, while the time base relates to the horizontal displacement. We start with A. Peak voltage is the highest voltage, so we find the amplitude of the wave. One division is 1 centimeter, and we are told 1 centimeter is equal to 1.5 volts. The amplitude is 2 boxes, or 2 centimeters, and that means peak voltage will be equal to 1.5 times 2, which is 3 volts. B. Frequency. This is the number of cycles per second. On the graph, 1 cycle ends here. These are 4 divisions of 4 centimeters. We are told 1 centimeter is equal to 2 milliseconds, or 0.002 seconds. So 4 centimeters will be equal to 4 times 0.002, which gives us 0.008 seconds. We say 1 cycle is equal to 0.008 seconds. How about 1 second? So we have 1 cycle times 1 second over 0.008 seconds. The seconds cancel out and we have 125 cycles. So we have 125 cycles per second, and that means the frequency is 125 Hertz. Alternatively, we could first find the period. It will be 4 times 0.001 seconds, which is 0.008 seconds. And then frequency is equal to 1 over period, which is 1 over 0.008, giving us 125 Hertz. Finally, the television tube. Now, the television tube is a cathode ray tube with a few modifications. First, the deflection system is made of magnetic fields. Magnetic fields are preferred to electric fields as they give wider deflections, which makes it possible to work with a wide screen with a relatively short tube. The video signals sent out from the TV transmitter are applied across the deflecting plate. The TV screen contains an array of tiny spots. Each spot is composed of 3 phosphor dots representing the primary colors, red, green, and blue. When the electron beam strikes the spot, it glows red, blue, or green depending on the phosphor on which it strikes. If the beam of electrons is incident on more than 1 phosphor in a spot, then a secondary color is seen. This causes the spot to race across the screen in a sequence of horizontal lines called the raster. Therefore, a combination of 3 primary colors in proper proportions can produce a colored picture on the screen. When viewed from the front of the screen, the spot moves in a pattern similar to the way your eyes move when you read a single column of a text. The scanning takes place at such a rapid rate that your eyes see a constant image over the entire screen. So the cathode ray tubes are adopted to act as picture tubes in television sets.